So we wanted to take this chance to kind of address some of the common reasons we're going to see up when we start working with proofs that involve angles. And there's going to be some similarities with the common reasons we see in proofs involving segments. First off, we're going to see a lot of definition of congruence because it's the most common way we're going to be moving. It's the most common way we're going to move between talking about shapes being the same and talking about numbers being equal. And we want to be able to make this movement because we can't add angles. We can add the angle measures. And that's a very small but really, really important detail. We can't add shapes. We add the measures of those shapes. So if I say two angles are congruent, the definition of congruence that allows me to then say, well, then the measure of the first angle equals the measure of the second, and I'm now dealing with numbers that I can add, subtract, multiply, etc. We'll see a lot of the definition of angle bisector. This is kind of like how we see definition of midpoint when we work with segments, because a midpoint divides a segment into two congruent pieces, while an angle bisector divides the angle into two congruent pieces. This is kind of a very small one, but we deal with a lot of right angles. And if we want to talk about the fact that a right angle is 90 degrees, but they don't tell us it's 90 degrees, they just tell us we have a right angle, we actually have to take a step to say, well, if you tell me it's a right angle, then its measure is 90 degrees. Again, talking about a right angle is a shape, its measure equaling 90 degrees is a number. The angle addition postulate is very much like the segment addition postulate, but with angles. Because we can't add angles together to get a larger angle, we add their measures. So this is another way for us to move from talking about shapes to talking about numbers. The definition of supplementary. Remember, it's the sum of the measures of supplementary angles is 180. We're not adding the angles together, we're adding their measures. So again, these are numbers. We don't see the definition of complementary angles quite as much. We'll see it a little bit early on, but as we move deeper into the course, the definition of supplementary shows up a lot more. And then what is technically the vertical angles theorem? I've mentioned briefly when we learned about vertical angles that vertical angles are always congruent. That's actually a theorem. We actually kind of informally proved it when we were going over that. But we see a ton of vertical angles, so get used to just saying vertical angles are congruent. Some other theorems that are on your sheet, and I just wanted to expand upon a little bit. Several theorems involving right angles. A lot of these feel like they're kind of obvious, but these are theorems. We can prove them true. They're not postulates. So perpendicular lines intersect to form right angles. That's a theorem. All right angles being congruent. We are going to use this one a lot because it saves us some steps in a proof of saying, well, if I have two right angles, their measures are both 90 because of the definition of right angles. And then if their measures are both 90, by substitution, the measures of the angles are equal to themselves. And then by the definition of congruent, the angles are congruent. If I have two right angles, I have a theorem that says, well, if I have two right angles, they have to be congruent because all right angles are congruent. Perpendicular lines form congruent adjacent angles. If you just draw a picture of this, you'll see why this is true. The next two are actually almost the same. If two angles are congruent and supplementary, in other words, if they have the same measures, and their measures add up to 180, well, the only way that happens is if both measures are 90, meaning they're both right angles. Well, then if two congruent angles form a linear pair, well, that means that I have two congruent angles that are supplementary and adjacent. Them being adjacent doesn't affect their measures, so it turns into a slight extension of the theorem above it, and they will each have to be right angles. The two that are a little bit tougher on your sheet are called the congruent complements theorem and the congruent supplements theorem. The congruent complement theorem says if two angles are complementary to the same third angle, then the first two angles are congruent. And what's happening here is, let's say I have angle 1 and angle 2, and then I have a third angle, angle 3. And I say, well, we know, in other words, we're given angles 1 and 3 are complementary. In other words, the measure of angle 1 plus the measure of angle 3 is 90. And then we're given that angles 2 and 3 are complementary. In other words, the measure of angle 2 plus the measure of angle 3 is 90. Well, then, this is two equations with two things I don't know, the measure of angle 1, the measure of angle 2, well, three things I don't know, and measure of angle 3. I'm going to take the second one, solve it for the measure of angle 3 by subtracting measure of angle 2 from both sides. That's our subtraction property. I'm then going to substitute this into my first equation for the measure of angle 3, and that's going to give me the measure of angle 1 plus 90 minus the measure of angle 2 is equal to 90. I then am going to isolate the measure of angle 1, so subtract 90 from both sides, subtraction property, and then addition property, add the measure of angle 2 to both sides, and then I have the measure of angle 1 is equal to the measure of angle 2, but by the definition of congruent, that means angle 1 is congruent to angle 2. So this was an informal proof because I wrote my steps, but I spoke my reasons. But notice I gave a reason for every single step. So angle 1 being congruent to angle 2 means that if angles 1 and 3 are complementary, and angles 2 and 3 are complementary, that means angles 1 and 2 must be congruent. Now that's going to feel a little bit weird because it feels like it's sort of like the transitive property, and it feels like we should be able to say, well, if 1 is complementary with 3 and 2 is complementary with 3, then 1 and 2 should be complementary. That's false. This says if 1 is complementary to 3 and 2 is complementary to 3, then 1 and 2 have to be the same. The congruent supplements thing does the same thing, but supplementary. So it would say if angle 1 and angle 3 are supplementary, and angle 2 and angle 3 are supplementary, then angles 1 and 2 must be the same. I did want to do one quick example in this video. So we have this picture. We're being told that angle QVW, which is right here, so that's QVW, and angle RWV is right here, they're supplementary. And we want to prove that angle QVP, QVP, which is adjacent to the purple, and angle RWV, my orange, are congruent. I will do this as a two-column proof so that you can see what that looks like. So in a two-column proof, the left-hand column are my steps. My first step is always my given. So we're told that that is supplementary, and that reason is given. So then I know eventually I want to get to the point of saying that my blue angle and my orange are congruent to each other. So QVP is going to be my blue angle. Well, looking at my picture, I can see that the blue and the purple are supplementary. So I'm going to say that angle QVW and angle QVP are supplementary. In terms of a reason, I can say that it's the definition of a linear pair because those are a linear pair. I could just write in my own words that together those two angles make a line. That would be correct as well. And I'm going to choose to say it that way. So together these two angles make a line. So then I have a few options here. I'm noticing that angle QVW is supplementary to two other angles. So my orange is supplementary to the purple, and the blue is supplementary to the purple. Well, this is the congruent supplements theorem I just went over. So using the congruent supplements theorem, I am able to say that angle RWV is congruent to angle QVP, which is what we were being asked to show, and that is the end of my proof.